The first speaker is Sebastian Harris from Rogelberg. About this explain.
Yeah. So let me start by thanking the organizers for making this nice conference possible in the first place, and then also for allowing me to participate not only by listening to all the great talks, but also by sharing a little bit about my own work on sparsity in the numerical 6-point bootstrap and novel extreme correlators in one dimension. So my plan is that in the first half of the talk, I say some general things about numerical 6-point bootstrap and how to set up a semi-definite program that's dual to 6-point crossing. And that part will be based on some work with Antonio, who's over there, upper team Kaviraj, and my PhD supervisor, Volker Schumerus. And then in the second part, I'll talk about some recent work that I put in the archive earlier this month, where I use the sparse structure of the semi-different programs that arise in the 6-point bootstrap in order to improve the numerics both on a quantitative and qualitative level, which ultimately allowed me to study some deformations of generosity Boson and generosity fermion that I come to in more detail later on. All right, but before I say how to 6-point bootstrap, I should say a few words about why to 6-point bootstrap. And my general take on higher point conformal bootstrap is that, well, in principle, of course, all of the crossing relations of 4-point functions already encode everything that crossing knows. So in principle, if we were very, very powerful, we could study very, very large systems of very complicated 4-point functions and would learn everything that crossing knows. But of course, in practice, this cannot be done, and we cannot just study, infinitely large systems with all of the correlation functions we want. So we need to find clever ways to access the data more efficiently. And one possible way might be to study higher point correlation functions of simple operators instead of complicated 4-point functions with complicated external operators. And this idea has been developed, I'd say, in two largely independent directions in the numerical bootstrap literature. So there's this truncated 5-point bootstrap by David Poland and Peter Tadic and Valentina Prilepina, where the aim is, you take a 5-point function, you truncate the crossing relations of the 5-point function, and you compute numerical estimates of OBE coefficients and principally also scaling dimensions with some heuristically estimated error bars. And the other direction, that's one that I talk about today, is this semi-definite 6-point bootstrap, where you start with a semi-definite dual formulation of the crossing relations of a 6-point function and compute some rigorous bounds like the one shown in this picture. So why do I say that these are, it's nice that Rajiv came right now because he's going to appear on the next slide. So why do I say that these two things are complementary? So with the nice categories that Rajiv gave us to gauge the value of science, I would say that this truncated 5-point bootstrap goes in the direction of depth and breadth. So the objective is, you find some clever way of numerically estimating OPE coefficients by truncating these 5-point functions. Whereas the semi-definite 6-point bootstrap that I talked about today, on the complementary side, has the aim of going in the direction of breadth and new perspectives. And I want to find qualitatively new bounds using 6-point functions. So what do I mean by qualitatively new bounds? So my perspective on Bootstrap in general is, okay, on numerical Bootstrap is you have the crossing equation and you're able to ask some questions to the crossing equation, and the crossing equation answers with some bounds. And as I want to argue, studying 6-point functions, you can very naturally formulate different questions than for 4-point functions and efficiently get answers to those questions. And in particular, these questions will be of the type, well, 4-point bootstrap is good to answer direct questions on an OPE, so you can get bounds on the spectrum of operators in the phi times phi OPE of some field phi. And 6-point bootstrap is very natural to formulate questions on 3 consecutive OPEs. So you can answer questions like what's the certain gap in a phi times phi OPE. And likewise, while 4-point bootstrap is natural to bound 3-point functions, 6-point bootstrap is natural to bound 4-point functions. As I make more precise, once I now start talking about how a numerical 6-point bootstrap actually works. So yeah, the starting point in this talk, I will just consider a 6-point function of identical scalars on the line, like the most simple setup you could imagine. And I use these indices to denote where I insert them. So phi I is just phi inserted at xi, where xi is some point on the line. And when I have this correlation functions, I can insert projectors into conformal multiplets and decompose them into products of 4-point functions, as I do in this equation 1. So I get some sum over primaries O, and then for each primary, I sum over all of the descendants that generate the conformal multiplet, and end up with some decomposition to this product of 4-point functions, including some descendant of the operator O. And of course, there are various ways in which I can perform this decomposition. So graphically, the decomposition in equation 1 would correspond to something like this. So I take these 3 operators and fuse them into O, and these 3 operators and also fuse them into O. And I can do this in various ways. For instance, I can cyclically permute them operators and get this decomposition here on the right-hand side, or this decomposition on the left-hand side, and equating these things as usual gives some cross-link equations. So for instance, I can say this decomposition is equal to this decomposition, and that will in equations give an equation like this. So, and at this stage, okay, I put an equation because I wanted to write some explicit equation, but really everything that I want to say with this equation is just that you get some functional equation where the unknown is this fno of x or fno of chi. And this fno of chi will play a central role in this talk, so I should stress again, well, what is this fno of chi? This fno of chi is just this 4-point function, including 3 copies of pi, the operator O, and then the index n is for the nth descendant. And okay, you get some functional equation that contains this and depends on 3 cross ratios. Why 3 cross ratios? Because we study a 6-point function on the line, and there are 3 cross ratios for that. So
fno of chi for higher n is just a derivative of okay, right?
yes, essentially that's true. Yeah, I mean I say essentially because ultimately this depends on what kind of cross ratios you pick, and for the cross ratios that I work with, it ends up being chi del chi at the end. So
A derivative.
it's a derivative, a nth derivative. Yeah.
Curly else.
And these curly L's are kinematic prefactors. So the prefactor that I can pull out of a 6-point function in order to reduce it to a function of cross ratios. And you see here, I divided the 2 decompositions called by the L of chi, so that L of xi, so that it ends up on one side. But okay. But in any case, what I want to say is, I mean, the relevant information here is some functional equation depending on these cross ratios chi. In order to do numerics, as usual, we need to get rid of this functional dependence, and we can do so by acting with functionals on the crossing equation. And the functionals that I use are derivative functionals evaluated at a crossing symmetric point. And what's the crossing symmetric point here is chi1 equal to chi2 equal to chi3 equal to 1/3. And why do I do this? Because, well, you can sit down, you can look at the equation, you can act with the combination, del chi1 to the A, del chi2 to the B, del chi3 to the C on it. And what you will get is something that looks like equation 3. So you'll find some matrix M that, of course, depends on which kind of derivatives you took, M, A, B, C. And the entries of this matrix can be written down very explicitly, and they depend only on this dimension delta O of the operator that's exchanged. Well, of course, they also depend on delta phi of the external operator, but that's just going to be fixed. And this matrix is contracted with two vectors, as you can see. So it has these indices m and n that run over these indices that counted the descendant of the operator O. And therefore, I can also rewrite this as a statement that this thing is the sum of operators O, and then some vectors inserted in some inner product. And the sum of these inner products is 0, and that's exactly the kind of situation we want to be in if you want to do numerical bootstrap. One thing that I want to point out about this matrix that will be very important and that will allow us to actually make any progress is that this matrix is not just any arbitrary matrix, but it's going to be a banded matrix, and its bandwidth is bounded above by the degree of the derivatives. Okay, so once we have some rules like this for every combination of derivatives, we can pick some basis f lambda of some subset of these matrices that occurred in the sum rules, and then we can start formulating some bootstrap problems. So, for instance, we can exclude the assumption that the entire triple OPE is subset of some spectrum S by finding some linear combination of elements of this f lambda that is positive semi-definite everywhere. Well, positive definite everywhere on S.
Sorry, can I ask?
Yeah, sure.
Why do the metrics only depend on delta O and not say on all the OP coefficients which are exchanged in the 14th function you're applying them to?
Well, okay, I can go back. Because all of this information that you're referring to is in FO. So this is a purely kinematical object that essentially comes just from this central thing here in the middle.
You're not acting with derivatives of Fn or of chi3.
So that's an important point. So as Balt pointed out, Fno is just essentially the nth derivative of this 4-point function. So if I act with the derivative on Fno, I just shift the label Fn, and this can be absorbed into a matrix operation multiplied on the right.
But so it doesn't mean that different Fn's. So there are some linear dependencies in this vector Fn. Are you now going to treat this vector Fo as the components of this vector is totally independent,
Yes,
as we would do like with the p coefficients?
that's what I'm going to do. Yes.
But is this a reasonable thing to do?
Yes, I think so. So, I mean, I suppose, well, okay. There might be special situations in which there's some shortening and some primary vanishes and there's some null primaries, not primaries, descendants. But I mean, in the generic case, we don't know that something like this happens. And
So the function bound cross operations do not impose correlations on the derivatives of this particular point. Like they would constrain derivatives of other points.
yeah, well. No, so okay. So the statement that I want to make to be more conservative is that I don't know of a good way to use any constraints that you can get on the 4-point function to impose on this level. And you can already get some nice bounds by not using any further information on this FOM. Yeah.
We'll come back to it.
Yes. Okay. And well, so I said something about how to bound some spectrum, and then of course you can write some variations of this that also bound these vectors Fno, or the entries of these vectors. And the challenge in this game is that the matrices that we want to deal with now, so the SCPs that we want to deal with now, have some constraints that are 7 different constraints for infinite dimensional matrices, because this index m and n goes from 0 to infinity. Okay. So at this stage, I cannot directly put it in a computer, but I need to do something more. But we succeeded in putting it into the computer and getting rigorous bounds in this paper with Antonio. And I'm not going to say a lot about this. I'm just going to say the method that we used was some truncation scheme where it was very important that we have some good understanding on asymptotic conditions that need to be imposed on top of the truncation. And with these correct asymptotic imposed, we got some convergent algorithm that gave us some functionals for which we then afterwards in an independent step could really test that they're positive, so that we knew that we were getting bounds that can be trusted and that are Regis bounds in that sense. And this entire procedure, while it worked, still had several problems. And I think from a practical perspective, the most problematic thing was that because of the nature of the semi-definite programs that arise in this problem, you cannot really use SCPB to solve them. So SCPB really struggles if you give it very large matrices, very large sparse matrices. Whereas SCPA is fine with it, and you can just plug the SCPs in. And I mean, it's a multi-purpose semi-definite program solver that was designed to work on generic semi-definite programs such as this. So you can use SCPA. But the problem with SCPA, of course, is that its code hasn't been maintained for a long time, and most pressingly, there's no option in SCPA to have both parallelization and arbitrary precision arithmetic. So if you want to do any serious numerics with this, you're going to be stuck because you cannot use large computing clusters, but you can just use a single node on some machine, and there's no way of making progress, I think.
So you could use STPB, but it would be slow.
SCPB would be terribly slow to the point where, in this truncation scheme, you have some truncation parameters, and for the values, for very small truncation parameters, SCPB could still sort of handle, but for large parameters and as large as we needed parameters, it would just not even get to the point where it would converge to anything. So, yeah.
Is this a convergence issue, or what we call instabilities in the numerics?
Well, so, okay, I don't know what the precise reason is for why SCPB struggles with this kind of semi-different programs. I can tell you, like one fun thing that I tried out to see where the issue lies is you can take the very simple semi-different program of just saying, take a large n by n identity matrix and ask what is the largest value of lambda, such that I can subtract lambda times another identity matrix. So it should be 1. And SCPA has no problem in telling me that. It tells me quite immediately. But SCPB for large values of the size really struggles and takes forever to solve this problem. So I think this quite nicely shows that there's some issues, but okay.
So it's actually not in inversion of the matrix. Instead, it's just in step length test. When you invert the complement, it's totally fine. Is this the case?
Wait, I don't understand the question. Sorry.
But maybe we shouldn't dwell on this too much.
Yeah, okay.
Because there's going to be some formal point.
Yeah. So ultimately, the point that I want to make is there are some issues and they're solved now. And they're solved by exploiting the sparsity structure. So what do I mean by this? Well, so the situation that we're in is we have this continuum of semi-definite constraints, but the constraint with infinite dimension matrices, but the matrices are some banded matrices. So they look something like this, for instance.
Sorry, are they polynomials in those?
Pardon?
Are they polynomials in those?
They're essentially rational functions of data, yes. There's some prefactor, but okay. And okay, so however, so there is some it's a common known fact in sparse semi-definite programming that whenever you have some semi-definite programs involving large sparse matrices, it's possible to reformulate these in terms of a couple of semi-definite programs involving smaller dense matrices that are coupled together. And in the particular case of banded matrices, the way this is going to look like is essentially I can trade the semi-definite constraints for these large banded matrices with some semi-different constraints that positively only involve the 3x3 blocks in the middle here that constitute the non-vanishing entries. So I can rewrite this semi-different program as another semi-different program that only has 3x3 matrices as constraints. So see these are exactly the non-vanishing blocks from the previous slide. And the price that I need to pay, of course, is that I don't only have one single semi-definite constraint for one of such matrices, but I have a discrete family of these constraints. And effectively, in other words, I get a new parameter, let's call it J, for instance, and I need to ensure positivity of these 3x3 matrices, not only for all values of delta, but also for all values of J. But that's not a big deal because, I mean, problems like this, as you all know, are exactly what SCPB was designed to excel at. Because this now, if you didn't know that this was a 6-point bootstrap talk, you would probably guess that this was me talking about some mixed correlator bootstrap in, say, 2D, where this J would have the interpretation of spin. Of course, it's in this context, it's not spin, it's just some auxiliary parameter.
Is this a relaxation of the original problem?
It's not a relaxation, so you can, yeah. So there's a theorem that you can for sparse matrices write down appropriate dense matrices such that the dense semi-definite programs are equivalent to the sparse one. So, yeah. In a fashion that's qualitatively looks like what I said.
Is it a deep result or is it something?
I wouldn't say it's a deep result, no. So it's, yeah, it's you do some computations and you can see it maybe a proof in one page or something like this. So I mean, you find it, and there's some nice reviews of sparse semi-definite programming that I cite also in my paper on this, where they explain very nicely, also in the most general setup, where you don't just have a banded matrix, but some arbitrary sparsity pattern. But yeah.
Is this a statement about the whole program, or is it from taking that if this matrix is called with semi-definite, then this matrix is about semi-definite, and this is it?
Right. So there's one direction that's kind of obvious, as you pointed out. So if I manage to find positive semi-definite matrices, 3x3 matrices like this, then I can sum them up and I can deduce that the original matrix was positive semi-definite as well. But there's the other way around that's more complicated, and the other way around, however, you can also see by doing some.
Standard directions.
Well, because
What?
these
No.
matrices have linear constraints.
Yes.
You see the x2.
So if I have,
Second matrix, same as in the.
This is just something.
well, I can.
Anyway, my question was, do you need to deal with the whole semi-definite program, and this is some statement about the program, or this is just a statement about the matrix being PSD denominated in some other matrix?
Yeah, it's a statement about, as you said, a statement about some matrices being positive semi-definite if and only if some of these dense matrices are positive semi-definite. But this then, of course, implies that for semi-definite programming, you find similar statements. Okay.
It's probably obvious and I missed it, but why 2D?
Well, I just said 2D because in 1D I don't have spin, and in 2D I don't
so
have spin as a discrete parameter. But that's just, I mean, don't take this too seriously. It's just a word that I put there. Right. So, however, what I wanted to say is that this now allowed me to use SCPB directly and use all of the power that it has to parallelize on classes and so on. And finally, I'd like to show you one example of how I applied this method. There's a nice 1D bootstrap problem that's been studied, for instance, in this paper by Miguel and Bernardo, where your parameters are, well, the external dimension of some field phi whose 4-point function you studied, as well as the dimension of the first non-trivial operator that occurs in the phi times phi OPE. So you have these two knobs to play with, delta phi and delta phi squared. And for fixed values of these two parameters, you would like to maximize the OPE coefficient C phi 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 squared. And you can do that, and you get some answers. And the answer that you get is essentially that if data phi squared is equal to 2 data phi, this problem is solved by the generalized free boson. If data phi squared is equal to 2 data phi plus 1, it's solved by a generalized free fermion. And there's some extreme correlators that interpolate between them. And you can even go one step further and give some degree of a meaning to the interpolation by looking at perturbation theory around the generalized free boson, massive free boson in ADS2, where you can compute how the dimension of this data phi squared should change, and how the OP coefficient should change as you turn on the phi to the 4 deformation, and you find that it matches essentially the bound.
Delta O is delta phi.
Yes, so this plot here is taken from that paper where they have different notations, but delta O is data phi squared, and AO is C phi squared, and delta 1 is the next operator.
And you want to say that delta phi is 1.
Yes, delta phi is 1 in this plot, so 2 delta phi is 2, and 2 delta phi plus 1 is 3. Thank you. Right, so this is some 4-point bootstrap problem, and once you got the answer to this, you can start thinking, okay, can I somehow try to extend this and give some meaning to this correlators beyond just saying, okay, it's some 4-point function, and can I extend it to maybe some full set of correlators or something like this? So the step that I looked at is the question, is there a natural way to extend this 4-point functions into 6-point functions as well? And for this, I would propose the following problem. So some 4-point maximization. First, we maximize the 3-point function. Now we maximize the 4-point functions. And the parameters are, again, data phi and data phi squared. But additionally, you can now also play with the dimension of the first operator that occurs in the phi times phi times phi triple OPE, which I call phi cubed here. And you can ask the question, okay, for a given data phi and data phi squared, assume that we know that this 4-point function is the one that we found using this 3-point maximization. Under this assumption, what is the maximal value that we can find for the 4-point function phi cubed 5, evaluated at 1/3 here? And you can plug it into a 6-point bootstrap that I've described, and you find some bound. So now this is the 3-dimensional plot because I fixed data phi to some small value. And data phi squared and data phi to the 3 are some parameters that I can vary. And on the z-axis here, I show the bound that I get. And again, if you're at the point, this corresponds to generalized free fermion, where data phi squared is 2 data phi plus 1, and data phi cubed is 3 data phi plus 3. You find that the bound is saturated by the 4-point function of phi and phi cubed in the generalized free fermion. And at the generalized free boson point, it's saturated by the generalized free boson. And between those, you now find a 2-parameter surface that interpolates between
Delta phi.
data phi in this plot. It's, I think, 0.01. Yeah. So that's why here you get very close to. Yeah.
Why is it small?
Why so small? Because, I mean, as I will get to this on the next slide, so maybe I say it here. So let me first say, as in the 4-point maximization, 3-point maximization, you can also think about what does this surface mean away from the generalized free boson, generalized free fermion. And for instance, what you can do is you can write down the phi to 6 deformation now in ADS2. Yes. Okay. That's quite good. And you can.
Sorry, let me interrupt. If people want to go downstairs, we've agreed that the next stop starts at 45. So there's no need to rush. You can just.
So you can ask the question, what's the derivative of this bound that I got on the 4-point function with respect to the triple trace dimension, that was a parameter that I could vary. And you can compare this with how the phi cubed 4-point function varies under this phi to 6 deformation. And okay, it's if you do this to first order lambda, it's some simple commutation where you just decompose some Witten diagrams into conformal blocks. And the answer that you find is that indeed these two things, so the variation of the bound and the variation of the 4-point function with respect to this phi to 6 coupling agrees quite well. And now we get to the point that Bart wanted to hear about. So you see here now I didn't fix data phi, but I varied it. And you can see for small values of data phi, it matches directly quite well. For larger values of data phi, it doesn't match well. And why is that? I mean, it's a typical thing that if you work with derivative functionals, increasing the external dimension quite, leads to slowdown of the numerics. And yeah.
Is the perturbator, I mean, it seems like you have point both of them below the red line. So I would assume that this means that it's the perturbation theory that is not accurate anymore.
No, because this is not a bound.
What?
This is not a bound. The bound, this here was a bound, and this was a strict bound where the green and the red blue dot, no, the red and the blue dot need to be below the bound. Here, however, I'm not plotting a bound, but I'm plotting the derivative of the bound with respect to the triple trace dimension, and I do this at some finite truncation of the numeric, so there's no reason why the analytic point should be either above or below the bound. But what I wanted to say is, as usual with derivative functionals, large data phi is somewhat problematic, and that's why also here I picked some small value of data phi so that we can see convergence faster. But maybe what's reassuring is that if I now increase this truncation parameter, so this would correspond to using 50 functionals, and this would correspond to using 25 functionals, the mismatch gets reduced. Okay. So yeah, this was one small application, and in view of time, I think it's good to now finally go to discussion. So, I mean, now that we can just use standard techniques of SCPB to solve these numerical 6-point problems, I think we're on a good way of making this applicable to some nice targets. But there's of course still a lot of work to do. And here I just listed two example applications that might be interesting to study in the future, which essentially could be studied with the techniques that are already there, perhaps with some minor improvements, such as for this example, we'd have to think about how to include supersymmetry and so on. And then on the other hand, there are also some general technical developments that need to still be pushed. So one nice thing is to think about would be to see how these bounds that have been found now in these functionals relate to some analytic functionals that maybe also solve this problem of large external dimension and slow convergence. An important technical point is that so far I haven't reliably extracted any spectra out of the extreme functions that I found, and improving on this would be of course quite important. And finally, going to higher dimensional CFTs to broaden the set of applicable cases would of course also be very interesting. Well, and with this, I'd like to thank you. And yeah, we can go to questions if there's time.
There was a paper a few years ago by Miguel and Sichuan, I believe, which bounded particular values of the 4-point function, but not using some 6-point method.
Yes.
Is it comparable what bounds you're getting to those?
So what I can say is that for the particular problem that I've shown you, I'm not sure how you would get the same bounds using their methods and how to get the same bounds using the 4-point bootstrap, simply because of the way that the problem is stated, and that I wouldn't directly know how to translate to these things from 4-point bootstrap. For the case where the two things are comparable and you could get some bounds that you from 4-point bootstrap that you could compare with the bound from a 6-point bootstrap, I think it would be very interesting to do that comparison, and that's something that should be done.
So if you increase the size of the matrix,
That's true.
grows. So how quickly does that?
Pardon?
How quickly does that kill you?
Yeah, so that's a very good observation. So, okay. As you can see, so for instance, for this bound, I think this was probably as far as I got. I went to lambda equal to 7, which was like 50 functionals. So the number of functionals was essentially quadratic with this parental lambda that it was cut off. And lambda is then exactly, so 7 by 7 matrices was still fine. And I guess if you want to push,
Size of the matrix.
pardon?
Lambda is exactly the size.
Lambda is exactly the size of the matrix, yes. And if I want to push, I guess I could also go to lambda equal to 8 still, because lambda equal to 7 was still something that could be done like within time scale of a week maybe or so, or two. But, pardon?
Laptop or on the cluster?
On the theory cluster at DC. Yeah, so yeah, that's a good point. This increase of the matrix size is some technical obstruction to increasing lambda as much as you would like.
Since you're not using the conformal position of the 4-point function, but only the relation between descendants, is it correct that this method would scale if you wanted to 8-point functions as well without some major change? Or
well, yeah, I suppose this is true. Like, I suppose you could take 8-point functions and decompose it into products of 5-point functions in an analogous way. There's maybe one important technical point that I remarked that I should make, which is that here you see it was important that in taking the derivatives of this FNO with respect to chi, I could remove all of the derivatives by putting it into some matrices that work with that shift around the n label. And that's essentially possible because in a 4-point function, I can put all of the kinematic dependence of this phi, pi, and phi into the O by a conformal transformation. In a 5-point function, this would no longer be possible. So this step might will be different, and this might affect the entire procedure quite heavily. But yeah.
Is it possible, at least in principle, to combine this with the 4-point function bootstrap?
Yes, I think so. So what you could do is you could study some mixed correlator system, for instance, where essentially you would do something like this. And complete and use essentially the 6-point function to complete the system involving the 5-point function into some positive definite matrix. Yeah.
And when you do this, would you do something different about FNs?
Well, so essentially what this would amount to is, I mean, this here would still be a product of FNs with FNs.
Yeah.
And here, this would be just a single line that goes, maybe I call it A and Fn and the OPE coefficient. And here again, an Fn OPE coefficient, and here, of course, just the OPE coefficient squared. So essentially, you would take this infinite matrix from the 6-point bootstrap and enhance it by a single row and column into a larger system. Yeah.
Okay, let's thank Sebastian again. So that some people have a chance to grow, but of course nobody. We have a very interesting talk coming up. Let's talk about this later.
Yeah.
Thank you. Because you are the next speaker.
No, I'm just very confident.
And we are so confident we are not doing these slides. No, we. So in that, like gravity.
Yeah.
Wait for 3 more minutes.
It's the same one as the top one, right? So please.
Yes, this thing.
I will try this.
But this is correct.
So we're not doing just
Critical is just the box. All right. What do you call it?
Yes, just how heavy are those correlators?
As heavy as you can imagine. Slava just made the exact same joke, by the way.
right. That's right.
Yes,
Very nice.
There's not so much light.
Yeah, I feel like
Maybe this one?
we should privilege the people here in person.
Okay. Here we can start. Gordon Rogelberg from Gale is going to tell us about MBCT correlators.
Hey guys, thanks for being here. Thanks, Sebastian, for the nice talk. My name is Gordon, and today I'm going to be talking about some recent work with David Poland on bootstrapping ICTP correlators, as well as hint at some ongoing work with David Poland and Li Wencheng. So the object of study in this talk is going to be a correlator of identical scalars. The kinematic prefactor stripped off, and then the goal is to better understand the space of these correlators.
So Gordon, I switched off the light because otherwise it's not gonna record it.
Sure, that's about it. The space of these correlators as we take the external scaling dimension to be very large. And this is towards the ultimate goal of studying genuinely heavy correlators where this external scaling dimension grows faster than the square root of central charge. In this talk, we won't assume the existence of a stress tensor in the Bootstrap equations. Essentially, the parameter of central charge doesn't enter, but we will be organizing constraints from crossing order by order in large delta O. Give some outline. We'll start with a motivating example. Given by these jet correlators in a generalized free field. So these are just a 4-point function of normal ordered products of generalized free fields. The purpose here is to identify some simple substructures which characterize these correlators as we take either phi to be very large or n to be very large. And ultimately, we're going to use these as a roadmap to interpret our Bootstrap results. Then we will introduce some formalism involving an OPE measure, which is a useful way of representing the conformal block decomposition when we take the external scaling dimension to be very large. We'll discuss some emergent symmetries of this measure, how these symmetries can be understood in terms of moment variables. And then we will ultimately use these moment variables, combining these constraints with the symmetries that we see and constraints of unitarity to derive some extremal solutions to the crossing equation at large external scaling dimension. And we'll include a bonus result in there as well. Then we'll conclude with some outlook. So again, maximize my space usage here. Great. Okay. So jet correlators. Right. So the physical picture of these jet correlators is that we place some of these product fields on the boundary. And these source a free gas of scalars which stream into the bulk and are transported along geodesic paths. And we can compute these all in a generalized free field by just using Wick contractions. And we find that they decompose into these nice substructures along with this combinatoric factor. And these substructures are called these fixed length blocks. And these are just written as a hypergeometric and are parameterized by K and delta phi. So why are they called fixed length blocks? Well, the reason why they're called fixed length blocks is that they repackage contributions to the OPE of operator families with a fixed length equal to 2K. So for example, for K is equal to 2, we'll have length 4 operators. And so these are of the form where each one of these brackets has their own double twist indices. And we call this a length 4 operator because it involves 4 phis. Great.
There's some interpretation in terms of this weak contractions, which weak contractions contribute to which HK.
Yeah, that's right. Yeah, so essentially, each one of these, when you expand out these hypergeometrics, they each are equipped with like this overall power of U over V delta phi to some K. And given some choice of normalization here, This is just associated with how many wick contractions are in like the S channel, something like this. And then, of course, you'll have other contributions here, but then these will end up being subleading in our normalization. All right, so now we want to answer the question of which operators contribute most to this OPE. So let's focus on the simplest 1D case. And what we want to study are these OPE weights. So this is just an OPE coefficient squared times the conformal block evaluated at z equals 1/2. You can choose other values of z here, but in this case, we're choosing z equals 1/2 because it's kind of this maximally non-universal part of the correlator where we're not particularly weighting more of the T-channel identity or more of the S-channel identity. And these OPE weights are supported on the spectrum of scaling dimensions in the OPE of external scalars. All right, so let's first take the simplest case of n equals 1. This is just the GFF correlator that we all know and love. And we can plot these OPE weights as a function of delta. And what we find is, okay, we have contribution from the S-channel identity, we have a contribution from the gap, and then we also have these higher contributions which fall off quite rapidly. So in other words, what we see is that when we have delta phi small, the correlator is very well approximated in this self-dual point by just the low-line conformal blocks. Right, so just these operators do a pretty good job of characterizing the entire correlator. And this is actually a very generic property shown by Krauss and Sivaramakrishnan in 2019. Now, on the other hand, let's take delta phi to be large. We see a very different story arise, where in addition to having a contribution from the S-channel identity, we actually have, you see that dominant operator contributions coalesce around this Gaussian saddle. So we have all these operators which are contributing to the saddle. The saddle is located at 2 square root of 2 delta phi and has a width of approximately square root of delta phi. And though familiar with some of these type of correlators, this saddle here is just associated with the T-channel identity.
What does it mean it's associated with this?
So if you just do inversion of the T-channel identity term, then you get all the operator contributions to the saddle.
Now you're at the 0.1 so.
Yeah, that's right. Yeah.
Well,
Well, in terms of you can compute the OP coefficients from that inversion, and you can compute the locations of the operators, and then you just multiply the OP coefficients times the conformal block evaluated at the location of that operator. And that gives you the OP weights.
but you're in GFF, so why do you know what the conditions are?
Yeah, yeah.
But, sorry, but what if we do the OP version for the very light operator?
Yeah. You don't have to use it. I mean, there's identities. I mean, we know exactly what contributions go into the T-channel identity. I'm just plotting them here.
But is there a chance that the light operator contribute equally?
Which graph is that? This graph or this graph?
No, because you are saying that you do the inversion on identity block in T-channel, you get this plot. But imagine you do the same thing on this the next non-trivial primary operator in the T-channel.
Yeah.
It's still light. Do you get the same plot?
Yeah, I mean, okay, so if you do that, then you're not just getting new operators, you just get perturbations on these operators. But yeah, I mean, you could do something like that. You would get perturbations on these, you would get anomalous dimensions on these operators and anomalous OP coefficients.
How is it expressed?
But what you're plotting is just GFF altogether.
I'm just plotting a GFF, yeah.
So there's nothing but the T-channel identity.
There's nothing but the T-channel, exactly.
Yeah, this statement strange, right? Because if you were to use the Lorentzian inversion formula here, the identity is the only operator that would contribute.
Sure. Yeah, this is just a very simple correlator that we're writing down. We're just kind of looking at some basic properties on the space of correlators. All right, so now let's take n to be greater than 1, take delta phi to be large. And we find that instead of just having a single saddle, okay, so once again, we have the S-chain identity. We actually have a bunch of these saddles. And each one of these saddles are in one-to-one correspondence with a family of fixed length operators repackaged in terms of these fixed length blocks. And the locations of these saddles are at 2 square root of 2k delta phi. And this dominant one is at 2 square root of 2n delta phi. So it's dominated by the saddle at k is equal to n over 2. And the reason for this is because of this this combinatoric factor. This is where the relative weights come from. Okay, great. So what do we learn from this? Well, okay, so we have this generic fact that when delta phi is small, we have light state dominance. And when delta phi is large, we have state dominance from states of with scaling dimensions of order of the delta O, so the total external scaling dimension. And we can also notice this simple Gaussian substructures that populate the OPE, which suggests that understanding this heavy OPE in terms of saddles is kind of a natural language for weakly interacting correlators. And sure.
Yeah, what is K?
What is K? So this is so we're have this decomposition in terms of blocks like this.
You have some saddles.
Yeah.
And then you said that one is 2 square.
Sorry, I was just this is just the generic center for the saddle coming from a block like this. So this is 2 square root of 2 delta phi n. This is 2 square root of 2 delta. I mean, okay, this should be 4. Then this should be 2 square root of 2, 3 delta phi, 2 delta phi. So
You say that one is square root of n delta.
this is just the one. This is the dominant one in the center.
2 times n over 2.
Yeah. So, yeah. And this point of studying the OP in terms of saddles is something that we expand more in our paper, where we introduce some deformations in these saddles by putting in a bulk contact interaction. So obviously not all heavy correlators are realized as a particular limit of a GFF. But we'll find that the space of correlators kind of coarsely spans the space of allowed correlators, which we'll see from our Bootstrap investigation.
But if you want to build a heavy external field, you can also take n variables.
Exactly. Yeah. So that's why we care about this family of correlators, because it's just taking a single parameter delta phi to be large, it only gives a single saddle, but really, we could expect these saddles to be anywhere in the OPE. So it just gives us 2 parameters where we can explore the space of heavy correlators. All right, so let's talk about the OPE measure. And so, and once again, let's restrict to the 1D case, just for make our formulas nice and simple. But we've worked this out in arbitrary dimension. And so everything is kind of generalizable, including bringing in spin into the picture. And we'll briefly talk about a result and involving that a little bit later. All right, so we have standard conformal block decomposition of this correlator. And we can just rewrite this as an integral over this positive measure times this ratio of conformal blocks. And for shorthand, when we're integrating something against this measure, we'll have to use this like Ritz functional notation. And so how do we define this measure? Well, we define it just so exactly reproduce the conformal block decomposition. And we have these delta masses. And it's easy to see when you integrate this against this ratio of conformal blocks, you just manifestly reproduce what we started with. Okay, so this is just defining the OP measure. Now let's do a change of variables, which maps z to this exponentiated and rescaled t variable, where again, delta O is the external scaling dimension. We'll introduce a rescaled scaling dimension, delta twiddle. And then we claim that for the dominant operator contributions to this OPE, this delta twiddle grows no faster than some constant. And the reason for this is we can use some OP convergent estimates. Basically say that for delta, any delta that grows faster than the external scaling dimension, these things rapidly decay as we take delta O to be very large. We'll also introduce a rescaled measure, mu twiddle, delta twiddle is equal to mu delta O, delta twiddle. Okay. So now let's do this change of variables, plug into here, and then take the limit that we take delta O to be very, very large. And we find at leading order, under this change of variables, we'll write GT. This correlator reads as the integral over this rescaled measure times e to the delta twiddle t plus some error terms. We'll write this first error term. We won't pay too much attention to the error terms here because we're just going to be looking at the leading order result. But needless to say, we have good control of these error terms. We can understand this asymptotic expansion very well. And we can make some quite precise statements in terms of this. All right, so now let's take t to live on some finite window.
Yeah, it's getting a little bit confusing.
The other one was worse, and so
Well, you could take the red one.
behind you.
Oh, gosh.
Oh gosh. The bloody board. Okay, I'll try this one for a little bit and then.
Okay.
There are more here as well.
All right. Oh, okay. You want to throw some at me?
Hey.
Most athletic physicists. It's not big. Okay, great. So let's just take t to live in some finite interval here, such that, this error term, we can essentially ignore this error term. And what we find is that we can essentially, oh, great marketing. We can essentially just view this correlation function under this change of variables as a moment generating function. Where we define these moments here as just integrating some power of delta twiddle against our OPE measure. Okay, so we've done a bunch of song and dance to cast this correlator as a moment generating function for the OPE measure. Now we can ask, well, how is this OPE measure constrained by crossing in unitary? Let's first think about crossing. So under the T-channel, the image under crossing, this kind of ratio block maps to, so it goes from e to the delta twiddle t to e to the 2 square root of 2 minus delta twiddle t. And then if we plug this into here, and then we do a change of integration variables, we find the following equality between moment generating functions. And by the uniqueness of the moment generating function, this essentially just equates this measure to its reflection here. And this extends to the OPE measure, the statement of reflection symmetry. First observed by Kim, Crabtree, Gurry, in 2016. Great. And on the level of moments, when we have such a symmetric measure like this tells us that that the odd central moments vanish. Or lambda odd. And this error term is rigorous when we treat these error terms with the respect that they deserve.
Your T cannot be too big because then your corrections are important.
Yeah, that's right. Yeah. So
Means that Z has to be close to 1/2.
yeah, so this holds true around this some small region near the self-dual point. Away from the self-dual point, we have better tools for understanding correlators when we take external scaling dimension to be large.
Imagine that the closeness of delta phi, like the distance between Z and half is controlled by how large the delta phi is, the external operator.
Yeah, and in this case, yeah, because we're rescaling the variable. But I write this notion of reflective symmetry. We're essentially equating these measures. We can't exactly equate these measures. The rigorous statement, and I'll just give a heuristic here, is that this estimate holds true for intervals around t equals 0 of size square root of delta O. And so if we integrate this against a Gaussian of a width square root of delta O, then it will Fourier transform into a Gaussian of size 1 over square root of delta O. So essentially, this statement, this equivalence of these measures holds true on intervals of size 1 over square root of delta O. So when we take delta O to be very large, it essentially just narrows into a delta function. So the statement becomes exact when delta O is infinite. Okay, so what about unitarity? Oh no. Like chalkboards and money.
Yeah, that's our catch.
Okay, so from unitarity, we have the fact that this OPE measure is positive definite and that it is supported above 0. So it's supported for the positive real line. And so we can take any polynomial in delta twiddle. We can square it, multiply it by some arbitrary power of delta twiddle, and integrate it against the OPE measure. And this thing will always be positive. Great. Okay, so we have these two constraints on moments. For those who are familiar with some moment problems, this just gives rise to the Hankel matrix positivity of moments. All right, so when we combine these constraints, we can actually derive as a two-sided bound on moment variables in the limit of large external scaling dimension. And so we find the following, that up to some error term, these new k's are bounded from above by 3/2k minus 1, and from below by 2 to the k over 2. And we'll label this lower sequence, this new k minus, and this upper sequence, new k plus. Okay. So we have these upper and lower bounds on moments, but how do we actually interpret them?
I think this is the best you can do with this method.
At leading order, yes. Yeah, these are sharp at leading order. This is some in the paper. At subleading order, we can also make some statements. It's less of a nice two-sided band like this, but yeah, there's some additional statements that we can make subleading order. But yeah, these are sharp. And we've also checked these numerically, and these rapidly converge, even for large delta phi.
I was just wondering, so you're basically saying that crossing is completely trivialized, it's just this reflection symmetry, there's nothing else You completely solve the problem.
At leading order. Leading order is the simplest possible case that you can get. At sub-leading order, it's a little more complicated. Right, but okay, so the nice part about these moments is that we can resum them into a moment generating function and take an inverse Laplace transform.
Just can
Yeah.
so when you solve this moment problem with this positivity, do you both cross reflection symmetry?
Yeah.
Okay. It's a combination of it.
Yeah, it's a combination of the two. Yeah. Right, so, okay, we resum these into a moment generating function, take the inverse Laplace transform, and then we can recover the extremal measures that are associated with these moments and attempt to better interpret them. And this gives us.
Is there a way to just reproduce the correlator to look at what kind of thing get the position space?
Yeah, that's right. Yeah. I mean, that's ultimately how we interpret the bounds is by just like taking a bunch of derivatives of the correlator and show that they reproduce the moment sequences. But it's kind of nice to also see what they actually mean on the side of the OP measure. So this upper extremal measure is after normalization is given by a single delta mass at 0 and a delta mass at 2 square root 2, delta twiddle. And this lower extremal measure, this one's already starting to die. It's just given by a single delta mass at square root of 2. Okay, so I can draw a little picture here. So in one of these cases, you have these two delta masses, 0, 2 square root of 2, and then one delta mass, square root of 2. Okay. So how do we interpret these measures? Well, okay, let's go back to our jet correlators, do this change of variables, and then take derivatives to reproduce these extremal moment sequences. And then we find, okay, so if we take this G1 correlator, normalize it, take a bunch of derivatives with respect to t, evaluate it at t equals 0, and then take the limit, the delta phi goes to infinity. We just recover our upper extremal moment sequence. And, this should be relatively clear because, after introducing this rescaled measure, this saddle, which had width of square root of delta phi, now has width 1 over square root of delta phi. So when we take delta phi to be infinite, it just narrows it to a delta function. And so this is just the S channel identity, and this is just the T channel identity. But then what about this one? It's a little bit trickier to notice. So here we look at the GN correlator. Take a bunch of derivatives with respect to t, evaluate t equals 0, and then we take the limit that n goes to infinity. And so, well, I'm gonna guess the punchline. This just gives you the lower sequence.
I see that paper.
Thanks. Right, and so then the reason why we just have a single delta function at square root of 2 is just coming from this combinatoric factor that arises in the decomposition into fixed length blocks after, again, rescaling by this total external scaling dimension. This just narrows into a delta function around k is equal to n over 2, which just extracts this saddle here, which narrows.
I'm confused because you said that even for the correlator which you call G1, in the limit that delta phi goes to infinity, you were showing us in one of the first plots some Gaussian sitting at the dimension 2 square root 2 delta.
Yeah.
So why in that case you have a second delta peak at delta equals 0? We are not showing that peak in the plot. We're just showing a single peak.
No, I did right. This is the S channel identity.
There's a dot.
There was a dot.
It was a dot, yeah. It was a very small dot. I should have made it a bigger dot.
They make a thing.
Okay.
But maybe that dot had the same height as sort of this.
Yeah, it's a little bit higher because of the normalization. I mean, essentially the property is that when you sum over all of those contributions from the T-channel identity, it has the same weight as the.
Well, yeah, so here they seem to be getting the same, exactly like 1/2.
Yeah, that's right. Yeah, when you rescale it, yeah, you just get delta functions. Yeah. Okay, cool. So this is a straightforward leading order result. We introduced this technique where we can write the correlator as a moment generating function. We constrain this moment generating function. Well, we constrain the OP measure using crossing unitarity at leading order. We can derive these strong upper and lower bounds, which are realized in terms of particular limits of GFF correlators. Now we can actually go a little bit further than this, and I'll give this this bonus result, which is obtained using constraints which are subleading around large delta phi, large delta O. And these actually bring spin into the picture. And not just a single spin, but actually the total angular momentum. This is actually kind of the natural variable to use around the self-dual point. And then we'll also do a rescaled spin. Uh-oh.
You're not in 1D anymore.
Yeah, this is a general dimension result. And what we're actually able to do is we're able to derive upper and lower bounds on the covariance in the OP distribution between delta twiddle and twiddle J2, which is some error term. This is bounded from above by d minus 1 over square root of 2, and bounded from below by 0. Right, so this is a correlator where when you study the OPE measure, the spin and scaling dimension are not at all correlated. And then here they are positively correlated with some maximal positive correlation. And we can also actually interpret these upper and lower bounds. And we find that this upper bound is also given by the limit of the G1 correlator as we take delta phi to be very large. And then this lower bound is saturated by this GN correlator as we take the limit of n to be very large. So not only are these correlators kind of extremal at leading order in large delta phi, they also appear to be extremal in some sense at subleading order in delta phi. But hopefully one would be able to even take this further and try to understand these constraints at subleading order and so on to try to get some insights into some other limits later. Okay.
You should be recommended.
Sorry?
You should start to give about.
Yeah, I'm just gonna do my outlook right now. So what's the outlook? Well, in some ongoing work with Liwan, we're looking at some numerical bounds on moments. So we derived some results for when scaling dimension is very large, but we also want to understand what are the constraints on moments where we take the external scaling dimension to be small. This is just kind of an interesting set of functionals that we can understand with the numerical bootstrap. We actually observe some interesting kink structure, especially on the lower bounds.
What dimension is this?
We could do this in general dimension. Yeah.
Yeah, I guess you have a structure in specific case.
Because it continues from the kinks like the cross limits.
Yeah. And then we can also look at some mixed correlators, trying to bound moments for mixed correlators systems. So in some soon to be upcoming work, we'll talk about some the aspect of having universal behavior away from the self-dual point of z is equal to z bar is equal to 1/2, away from the self-dual configurations. Actually, this should be extended to an entire line. But yeah, so the universal away from the self-dual configurations, especially when the correlator is bounded as we take external scaling dimension to be large. We'll make a more precise statement of reflection symmetry, which is valid for all external scaling dimensions, not just in the limit that we take external scaling dimension very large. That's what I was talking about earlier, where we're doing Fourier analysis here. And we'll talk about the emergence of dynamical phase transitions. In the limit that we take external scaling, which shouldn't be very large. And then towards our ultimate goal of better understanding genuinely heavy correlators in a gravitational sense, we'll do some OP measure analysis of multi-stress tensors. By way of studying these heavy vacuum Virasor blocks. In 2 dimensions. And with that, I can conclude the talk.
There are already a bunch of questions, maybe it's over time, but okay. Can we connect predictions from ETA to?
That's a good question. So that seems to be something that will show up in this multi-stress tensor analysis. I think there's some soft theorems about which kind of operators, which kind of heavy operators stabilize. And it seems like understanding these families of multi-stress tensors is kind of a useful way of doing that through some work by Peter Tadich himself. And then the other way that one could try to approach these heavy correlators is by studying a 2-point function of heavy operators at funding temperature. And so we're also kind of interested in trying to understand these asymptotic constraints that come from when you have some thermal effective action and couple some 2-point function. Yeah.
So if you use the z equals 1 z equals 1/2, you get these constraints, and you happen to get multiple constraints where you know the endpoints the theories. If you change this, if you would do somewhere, is that the right choice of right choice, or what happens if you choose something else?
So if you look along this Lorentzian self-dual line where z is equal to 1 minus c bar, this does seem to be kind of the optimal set of constraints that you get. These are kinematic dependent. This is unique to z equals 1/2. But we can generalize this result to moving away from the self-dual. When you kind of move away from the self-dual line, you start to expect more universal behavior arising in the correlator that comes from either getting a lot of the T-channel identity contribution, the S-channel identity contribution. And so staying near the self-dual line seems to be kind of this maximally non-universal place to analyze these heavy correlators. But you can also, you can write down the statement of reflection symmetry for arbitrary kinematics by just doing kind of a shift of the change of variables that we were talking about before. You're just Taylor expanding around a different location.
Coefficients, but heavy with different scales.
So it depends on what you mean by that last heavy, because we can consider OP coefficients which associate with operators that grow much faster than the external scaling dimension, or we can consider heavy operators which grow of the same order as the external scaling dimension. And so near the self-dual point, we're going to get information about operators which grow around the same rate as the external scaling dimension. But if you want to understand operators that grow with scaling dimension that grow much faster than the external scaling dimension, then you would want to use something like Tauberian theory, and that gives you access to those types of OP coefficients.
So there is no precise time at this point that the scaling is of some power.
Yeah, that's harder to do with this formalism, especially because we're kind of combining the value of the conformal block times the OP coefficient. And so we're essentially removing the kind of normalization dependence that we have in the OP coefficient by combining these two. But obviously, if you are able to recover an extremal measure exactly, then you can just divide it by the conformal block evaluated at z equals 1/2, and then that gives you the spectrum of OP coefficients.
I think maybe you should thank again Gordon and go for the coffee break. That's just